Okay, this is lesson 44, applying similarity. Theorem 44-1 says that if two polygons are similar, then the ratio of their perimeters is equal to the ratio of their corresponding sides. And I'll explain that here in a minute as we work an example down below. But before we do that, I want to start with some review. So it says here the hexagons in the diagram are similar. Now remember, similar means that the sides are proportional, the angles are congruent. Okay, so it's two of the same shape but different sizes. And they want us to find the values of x and y. All right, so just by looking at these two hexagons, we can see that this side corresponds with this side. This side corresponds with this side. And this side corresponds with this side. Okay, that's going to be very helpful because remember the sides are proportionate, so we can set up proportions, two fractions that are equal to each other to solve for x and y. And so we're going to start with the green because they give us two values to use, 20 and 8. And then we can set up x over 6 to find x. And then later we'll do 20 over 8 again, but this time we're going to use 15 over y to solve for y. But I want to remind you that you have to follow a pattern when you set up these proportions. So if you're going to do 20 over 8, you have to then start with x over 6. Okay, same way with 20 over 8, you got to start with the 15 over the y. You can't bounce around. Now, once you have those proportions set up, then you cross multiply to then solve for x. So we have 8 times x, which is 8x, 20 times 6, which is 120. When I divide both sides by 8, I get x equal to 15. Okay, so I've solved for x. Now let me solve for y. So 20 times y is 20y. 8 times 15 is also 120. Divide both sides by 20 and I get y equals 6. Okay, so that's just a review on similarity. Now, look over here where it says that pentagons ABCDE and FGHIJ are regular pentagons. I'm going to stop there for a minute because it's important that we know what regular means. If you think back on a past lesson when we talked about regular and irregular shapes, regular means that the sides are equal. Okay, so equal sides. That's going to be important whenever we solve for y later. All right, so let me keep reading the rest of the problem. It says the similarity ratio of these two pentagons is 3 to 2. That's important because we need that information to solve. Find the values, once again, x and y. So make sure you solve for both. All right, so I'm going to use my highlighter again, and I'm going to highlight the sides that correspond. So notice those two go together. All right, and they gave me the similarity ratio of 3 to 2. So I'm going to set it up as 3 to 2 is equal to 12 over x squared plus 4. Be very careful when you're cross multiplying, okay? You must distribute this 3 to both terms, x squared and 4. So don't accidentally skip that step. So here we have 3x squared plus 12, right? Because 3 times 4 is 12. And then cross multiply the other way, 2 times 12 is 24. So if I subtract 12 from both sides, I get a positive 12 on the right. Divide both sides by 3, and I get x squared equal to 4. Take the square root of both sides, and I get x equal to 2. Now, don't be tempted to box that because that's not what they're asking for. Well, actually, yes. Find the values of x and y. So we found x, but now we have to find y. And that's where this comes into play, where regular pentagons tells us that the sides are equal. So if this is 12, this is also 12. So I can set this equal to 12 to find y. So I'm going to do that. 3y minus 6 equals 12. Add 6 to both sides, I get 18. Divide by 3, and I get y equal to 6. All right, so moving on to this question right here. What is the ratio of the perimeter of the two pentagons? That's where we come back up here and apply this theorem. It's telling us that the perimeter ratio is equal to the corresponding side ratio. Well, do you remember down here where it said the ratio is 3 to 2? Technically, if I know that theorem, I can just write down 3 to 2 and box it, because I know that the perimeter ratio is equal to the corresponding side ratio. But let's just say we wanted to prove it, or that we forgot the theorem altogether. We could say that the perimeter of the first hexagon is 12 times, or pentagon rather, sorry, 12 times 5 sides is 60. That's the perimeter of the first one. The perimeter of the second one is, first we have to plug in that 2 that we found for x, and then we have to multiply it times 5 sides. So here we have 2 squared, which is 4, plus 4 would be 8, and 8 times 5 is 40. So if I were to set up a ratio between the two perimeters, I would get 60 over 40, and if I reduced that, I would in fact get 3 over 2. But once again, like I said, if you know that theorem up above, you just copy the corresponding side ratio for the perimeter ratio. Okay, last problem on this page says figures HIJK and LMNO are similar polygons. Their corresponding sides have a ratio of 2 to 5. If the perimeter of figure HIJK is 27 inches, what is the perimeter of LMNO? Okay, so we're going to set up a proportion. We're going to be careful though, because this says 2 to 5 and the order matters. So 2 to 5. I'm going to write that over here so I can see that the 2 goes with HIJK and the 5 goes with the LMNO, because that matters. So 2 over 5. They gave us HIJK to be 27. So I have to put that next to the 2. So 27 over x. Cross multiply, we get 2x equals 135. Divide by 2, we get 67.5 inches. Because perimeter is in inches. And we'll even put equals LMNO, perimeter of. Okay, that is lesson 44. Moving on to lesson 45, Introduction to Coordinate Proofs. A coordinate proof is a style of proof that uses coordinate geometry and algebra. It's important to keep in mind that the easiest way to solve these is to place the vertex at the origin. So let's start off with two very simple examples. This one right here says that triangle ABC has a base of 4 and a height of 3. Angle A is at the right angle, and they want us to position it on the coordinate plane. So remember, like I said, start at the origin. So they told us 4 units to the right. That's the base, so that's easy. Just go 4 this way. They told us it's 3 units high. They tell us it's a right triangle, so let's just close it off with that hypotenuse. And they say that A is at the right angle. So B and C can be either one of these, but A has to be at the right angle. So we follow the directions. We place the right triangle with the base of 4 and a height of 3 on the coordinate plane. So we're finished with that one. This one requires a little bit more work. It's asking us to use the coordinate proof that's given to show that triangle HIJ is an isosceles triangle. Now, it's important that you remember isosceles means that these two sides are congruent. They're the exact same length, exact same distance. So the way we're going to prove that is we're going to find the distance of JI. Remember distance formula? That's what we're going to use here. And we're going to have to use this coordinate and this coordinate to plug into the distance formula. So I have here 3 minus 6 squared plus 2 minus 0 squared. And then we're going to simplify that. So that's negative 3 squared plus 2 squared, which ends up being 9 plus 4 squared, or square root of 9 plus 4. And then that gives you square root of 13. All right, let's see if JH is also square root of 13, and then we will have proven that it's an isosceles. Okay, so this time we are going to use, I'll use blue, this one and this one. Okay, so we're going to plug that into the distance formula once again. 3 minus 0 squared plus 2 minus 0 squared. That gives you 3 squared plus 2 squared. And that is, again, 9 plus 4, which is square root of 13. So notice they are the same distance, which means it is an isosceles triangle. The way you would show this on your homework is you would say C work on your front answer page, and then I'm going to be looking for this. I want to see that these two are congruent. All right, moving on to something a little bit more abstract, not very difficult, but it does require you to understand what's happening. So this one says a square, so you have to know a square has all equal sides, has a side length of A. They want us to place the square on the coordinate plane and label each vertex with an ordered pair. All right, so we are going to put, as best as we can, equal sides. We're not artists, but we can try. So here's our square. And we know this coordinate because it's at the origin. So we're going to label that one 0, 0. Okay? Now, they told me that it's A length, right? So this is A units. So this right here is going to be A units and then 0 for the y, because it's still at the 0 on the y-axis. Now, since it's a square, it must mean that I went A units up as well. So this is going to be 0, comma A, right? 0 on the x, right? That's 0 on the x-axis. And then A units on the y. Okay, that would have to make this coordinate A, comma A. Since it's a square, it means we went A to the right and A up, hence AA. Like I said, not hard, but a little abstract. So this one over here says, given the parallelogram OPQR, one side length labeled C, assign possible coordinates to the vertices. So let's start by drawing our parallelogram. Once again, we know this to be the origin, so we're going to label that AA. And actually, before I forget, I need to label OPQR because they gave me labels for the vertices. Okay, back to labeling. So they said one side length labeled C. So we're going to go C units to the right, which would make this C, comma 0. Now, this coordinate right here has to be two different letters, two different variables, because it's not an A, it's not a C. And actually, why did I write that? This is 0, 0 for the origin. Apologize for that, because this right here is going to be A, comma B. We could have used X, Y, anything other than C. Now, this one requires some thinking. This is C units to the right. But notice I need a little bit more to get up to this point right here. Well, this right here is the same as this right here. This many units A over. So that would make our first ordered pair A plus whatever C is. Then the Y value or coordinate is B, because B is here, B is here. That means this is B. It's on the same Y coordinate. All right, down here it says assign coordinates to the vertices of isosceles triangle STU with the height of 4 from the vertex. Okay, remember what we talked about as far as isosceles triangles are concerned. They have two equal sides. All right, so I'm going to label this 4 units, and I'm going to draw my isosceles triangle as best I can. They're congruent. Now I know this coordinate right there has to be 0, 4. 0 on the x, 4 on the y. This one over here, we don't know what the x units are, so we'll just use x, but we do know the y is at 0. So this will be x comma 0. And if it's the same distance apart on the other side, this has to be the negative, the opposite. So negative x, 0. Oh, and I forgot to label again, S, T, U. All right, last but not least, prove that the figure ABCD is a parallelogram. Remember, parallel. So if I can prove that this is parallel to this, and that this is parallel to this, then I will have accomplished what they're asking me to do. So in other words, we're going to write down, is BC parallel to AD? We're going to prove that. And is AB parallel to DC? All right, so let's take a look at these two lines. To get from B to C, I go up 1 and over 4. Up 1 over 4. So the M, the slope is 1 over 4. Let's see if that's also the slope from A to D. Okay, up 1 over 4. Yes, it is. So this one's also 1 over 4. So far, so good. Now let's do the same exact thing for these two sides. So from A to B, it looks like it goes up 4 over 1. So this is 4 over 1, or just 4. And then now we're going to do this line right here, up 4 over 1. Okay. So yes, this is a parallelogram. And on your homework sheet, you'll just say C work, and I will look for this. All right, last lesson for this set. Lesson 46, triangle similarity. You may remember that we've covered something like this already, but that was with triangle congruence. This is with triangle similarity, okay? So don't get the two confused. This first postulate says that if two angles of one triangle are congruent to two angles of another, then the triangles are similar. So this goes with angle, angle. Down here, we'll be dealing with side, 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 and side, angle, side. And I'll just cover those real quick. If the lengths of the sides of a triangle are proportional to the lengths of the sides of another, then they're similar. Do you hear that language? So that's why it's side, side, side. This one says if two sides of one triangle proportionate to two sides of another and the included angles are congruent, then the triangles are similar. So you hear there side, angle, side. All right, with angle, angle, when you look at this diagram, do you see this triangle overlapping this triangle? That means that they both share angle C. So there's one angle that they have the same of. Also, look at these feather marks here that tell us that these lines are parallel. And then right here we have a transversal. So this corresponds with this. So that must mean that those two angles are congruent, which is the second angle and the angle, angle. Knowing that, we know that these two triangles are similar, and therefore we can set up a proportion. Now I want you to notice something. Do you notice how the 3 over the 5 is the same as the 9 over the x, because they're trying us to find DE. So we're trying to look for this line right here. Now, I want you to pay attention that I said 9, right? Because a lot of kids will do 3 over 5, and then they'll do 6 over x. But we need the whole side, not just part of it. Okay, so be very careful when you set those up. It's 9 over x. And we found that by adding the 3 and the 6. And then from there, it's the same. We cross multiply. 3x equals 45. And then we know that x is equal to 15. And that was the side DE that they asked me to find. All right, moving on to side, 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 and side, angle, side. Show that the triangles are similar by side, side, side. Now, when you look at this, I want you to be careful. Can you tell that the two have been flipped? Meaning this goes with this. See how it's slanting opposite ways? So the safest way to prevent mistakes is to first start by writing out the triangle congruent statement. So for me, I wrote down triangle UWV is similar to triangle XYZ. Okay. Then from there, I can see, okay, UW goes with XY and WV goes with YZ. So it helps my eyes a little bit better. So let's prove they're similar by their sides being proportionate. So let's start with UW and XY. So UW is right here, so that's 2. And XY is right here, so that's 6. And if I reduce that, I get 1/3. Now let's see if the others are also 1/3. This time we're going to compare WV to YZ. Okay, WV is 3 and YZ is 9. So 3 over 9, which also beautifully reduces to 1/3. Okay, the last side we have to prove. VU and ZX. So VU is 4 and ZX is 12. 4 over 12 also reduces to 1/3. So because we have 1/3, 1/3, 1/3, we have now proven by side, side, side that they are in fact similar because they're proportionate. All right, over here, EX equals 6, ED is 11, and XY is 7. Find DF. Step 1, we always have to label the information that they gave us. So they said EX was 6, ED 11, and XY 7, and they want us to find DF. So super simple. We're going to do 6 over 7 equals 11 over X. We're going to follow that same proportion pattern. So 6 over 7 equals 11 over X. That gives us 6X equals 77, and X is equal to 77 over 6. And that is our answer. All right, those are the 3 lessons for this batch. Let me know if you have any